So this video is going to be an introduction to the forces springs generate and the amount of potential energy or work that a spring could do after being compressed. So the first thing to think about when we think about springs is something called Hooke's law. And Hooke's law tells us that the force a spring can generate is equal to negative kx, where k is the spring constant, which is determined by the type of spring it is. So different springs have different spring constants. You'd look that up in the springs manufacturing information, or it might be given to you by the problem. Every spring is different. Spring constant tells us how stiff the spring is. So if a spring is very stiff, it'll have a high spring constant. And if a spring is not very stiff, it'll have a low spring constant. Spring constants are usually measured in something like, in some units like newtons per meter, meaning that if I add a certain number of newtons to my spring, I will compress it x distance, or in meters. The next thing in the equation is x. This x is the amount that the spring is either stretched or compressed. So you'll see, if you look at this equation, that this compression and the stretching of the spring, or the compression or stretching of the spring is proportional to the force the spring can generate. So if I compress a spring twice as much, I'll see that it can generate twice as much force. If I compress the spring 3 times as much, I'll see that it'll generate 3 times more force, so it's proportional. The thing about this law that's really interesting is that it has this negative sign here. And this negative sign indicates that the spring's force will always be in the opposite direction of its displacement. So if you compress a spring, this negative sign tells us that its force that the spring will generate will be back in the direction that you compressed it. And if you stretch a spring, this negative sign says that the spring wants to return back to the position you stretched it from, right? So let's look at that a little deeper. And so the point that you stretch it from, or that you compress it from, of the spring is called the equilibrium point. And the equilibrium point is the point where the spring just wants to sit when it's not being stretched or compressed and there's no force acting on it. And we say that the equilibrium point in this case, or in all cases, is equal to 0, meaning that the spring is not moved in and it's not moved out. So in this diagram, what we've done is we've compressed the spring some distance x, which means that the force, according to Hooke's law, which tells us that the force of the spring is equal to minus kx. So since we compressed it some distance in, and that's telling us that if our x is negative in this case, and our k is negative, that the force we generate is going to be positive and in the outward direction. Okay? So the spring always acts toward the equilibrium point, away from the direction you either compressed it or you stretched it. So if you're acting on a spring with a force, what the spring is doing is it's storing energy, and that energy can then be used to do work or push something, right? So the energy stored in a spring is a special type of potential energy called elastic potential energy. And so we can find how much work or you're doing on the spring, and therefore how much elastic potential energy you're adding to a spring, by using the following equation. So we say that the work that you were doing on the spring is equal to 1/2 kx squared, where k is our spring constant, once again. X is our displacement of the spring. And W would be the amount of work we're doing on the spring. So if we do a certain amount of work on the spring, we're giving it potential energy. And this potential energy is our elastic potential energy. So let's apply this to some problem solving. So for example, in this example problem, we have a block with mass 5 kilograms that is attached to a horizontal spring with a spring constant of 4 times 10 to the second newtons per meter. The surface of the block is on a frictionless surface, so that's good, we don't have to worry about friction. And the block is being pulled out some distance, 0.05 meters, and then it's released, and we're being asked to find the speed when it reaches the equilibrium point. And so remember that the equilibrium point is x equals 0 meters. Okay, so right when it returns to x equals 0 meters, as shown in the diagram below, that's the point we want to find the speed. So let's start by finding all the energies that we are dealing with. So we're initially stretching the spring, and so that's doing some work on the spring and giving it some elastic potential energy. So we know we have potential energy of the spring, and when we start, that's the only energy this system has. When we let it go, all of that energy is going to be transformed into another kind of energy until it reaches the equilibrium point. It's going to be turned into kinetic energy, specifically kinetic energy of the box. Okay, so now that we've collected all of our energies, let's break this down. So the potential energy that we have in the spring is equal to 1/2 kx squared, and the kinetic energy of our box is equal to 1/2 mass of the box times the velocity of the box squared. Okay, we can cancel out some terms here, and we're gonna need to move some things around. So kx squared divided by the mass of our box, square root, is equal to our velocity. Okay, we can substitute into this. So we know that our spring constant was, hang on, I'm gonna move down here, do my math. My spring constant was up here, 4.00 times 10 to the second times x squared. So we displaced the spring 0.0500 meters squared, divided by the mass of our box, which is 5.00 kilograms. And we solve for that, and we find that our velocity is equal to 0.447 meters per second. Okay, so that's how we can use springs and spring constants and kinetic energy and elastic potential energy to solve problems.